Good afternoon, this is Dr. Heidelberg, and today's presentation will be finite element analysis in fluid flow. We will take a look at the typical partial differential equation used in fluid dynamics. We'll look at the strong form solution of the partial differential equation, and then we see how we discretize it into a weak form used in finite element analysis. Particularly, we'll consider the Galerkin solution method. We'll derive the matrix equation, we'll solve the matrix equations, and we'll compare the results to the exact solution. The references that we'll use in this presentation are listed over here. Some of them will be edited. Typical engineering problems are being characterized by governing equation. You see they all look similarly. The differences in parameters and the physical interpretation of the unknown variables. For example, in fluid mechanics, the unknown variables could be velocity, fluid velocity, or fluid flow, and the parameters that describe the phenomena include diameter, for example, in flowing pipes, cross-sectional area, and the viscosity. The finite element method uses the boundary conditions, embed them within the so-called strong formulation, and converts it into a weak formulation, which are algebraic equations that relate nodal values of the unknown variable to nodal force function at the continuum related by the parameters that describe the phenomena. To solve for the unknown nodal values, we invert the matrix, multiply it by the forcing function, and get the results. The continuum has to be defined in terms of the boundary conditions. There could be surface boundary conditions. There could be normal to the surface boundary condition, internal forces, or unknown variables and their derivatives on the periphery. The example that we'll take a look at is similar to what we saw before, second order partial differential equation. It's defined on a single axis from x equal to 0 to x equal to 1. It has boundary condition that at 0 the value of the variable equals to u0, and at 1 the variable of the derivative equals to q. Together, this is the so-called strong form of the formulation. To find an exact solution, we integrate both sides of the equation. The dx moves to the right-hand side, and then the integral of this variable becomes lambda du dx. Then f dx becomes fx plus a constant of integration, c1. And then integrating that again, dx put to the right-hand side, we get lambda u, fx becomes fx squared divided by 2, then c1 becomes c1x, and c2 is the second constant of integration. We recall that the boundary condition was that at x equal to 0, u was 0, u0, therefore C2 equals to lambda u0. This is what we have over here. And at x equal to 1, lambda du dx was equal to q. Therefore, C1 equals to q minus f, and that is the expression here. When we put these two values into the original equation, we come up with the exact solution relating the unknown variable to the independent variable x. To build the finite element analysis, we start by assuming a solution which consists of nodal values uk of the unknown variable multiplied times some trial basis function. The basis functions are typically polynomials or sine cosine forms. And when we plug in this assumed solution into the original equation that represents the phenomena, then u, which was originally here, becomes u hat. And then the whole expression does not equal to 0 because this is an approximation. It must leave a residual. And the whole process of finding a solution is to find a set of nodal values such that the residual approaches 0. And we can mathematically represent it by multiplying the residual times a weighting function, and the optimization process is generated by taking the integral of the weighting function times the residual and setting it up to 0. Now, in the Galerkin method, the weighting function and the base functions are identical. And then we use this equation in order to come up with algebraic equations, and then they can be solved to determine the unknown nodal values. And this Galerkin process can be used in solving any differential equations. For example, we can approximate the unknown variable with a polynomial going x and x squared. And then if we use the boundary condition, we could solve for one element, which is u1, and we still left with u2 as unknown. We use the other boundary condition by taking the derivative of the approximation and using the relationship that we had earlier, and we can find the other unknown, which is u2, and substituting u2 into the equation, we find the very same equation as we find an exact. Now, the reason why it is exactly the same is because our assumed solution was a polynomial, and we already find out that the exact solution was made of the same polynomial. In more general way, we discretize the domain in the process of finding a solution as our step one with finite elements. They have definitive size, and they have nodal at definitive locations. The presentation over here is the same as we had on the exact solution, going from x0 to x1. Then the second step is to use the weak formulation by minimizing the weighting residual or setting it up to 0. What we have here is the weighted residual that we saw earlier, and we have the assumed approximated solution plugged into that formulation. Now what we have to do is take an integral by parts of this form. To see how that works, we look at the derivative by parts of uv. duv equals udv plus v du. Therefore, if we take the integral of duv, it becomes uv, and then we rearrange the term, and this element over here, integral of u dv, equals to uv minus this term moves to the other side, integral v du. So in the Galerkin formulation, if we define u as being the shape function, and dv as being the basis equation, dx, and this will be v, then the formulation by parts makes this equal to uv minus integral v du. So what is uv? uv is W times lambda du dx. W times lambda du dx has to be evaluated at the two boundary conditions, minus v du, integral of v du. So v is lambda du dx, and w dw is dw dx, and you see it over here. And then we have a leftover integral of wf, which is carried over here with a minus sign. This has to be 0, and we rearrange the term, and we find out the weak form of the same equation that we saw previously in exact. We can place the expressions for lambda du dx at the nodal value by the quantity q at the nodal value for each element, and then the expression of the weak form is simplified. This is exact same expression before, but instead of having the expression lambda du dx, we plug in q, and we come up with this expression. And the simplification in the Galerkin method is that this weak form already includes the boundary condition, and the order of derivatives is reduced by 1. We no longer have a second order equation. Now expressions are only first order derivatives. The next step is to define the weak form in terms of the approximated functions. So over an element, we define the unknown variable as the sum of two nodal variables at the end of the two end element times 2 the base functions phi. And we see the base function here, which according to the Galerkin method are the same as the shape function. And if you look at the first equation over here of this shape function, it's a polynomial of order 1, and phi1 equals to xe minus x divided by delta xe. Delta xe is the length of the element. And we see that when we place the value of xe in this linear function, then phi1 becomes 0 at xe, and if we put over here x equal xe minus 1, then xe minus xe minus 1, this is exactly this length, which is delta xe, we have a value of 1. So this shape function is a linear line which has a value of 1 at one node and value of 0 at another node. And it will take any value of the unknown function at the nodes, and we will actually spread it linearly over the element domain. So when we use these expressions in the Galerkin equation, we come up with this expression with the q values at the nodes of the elements. When we make the identity of the shape function and the base functions and plug it into the weak form equation, then we eliminate together the w's, and everything now is written in terms of the base function phi, and what we end up with is an expression over here that could be used for the two nodal nodes of the elements, two equations that can be converted into an algebraic form. Here's one equation, and here's the other equation, and it includes the boundary values and also the shape functions as part of it. We can now simplify these equations and write them in a matrix form where we have the nodal values of the unknowns multiplied times the matrix of the element equals to the nodal values of the Fourier function and the boundary conditions. Now the explicit components of the K matrix are given by taking these elements. Now phi is a linear function, so finding the derivative of a linear function is easy. Finding the integral of a linear function is easy, and we can now construct the matrix for the finite element formulation. Here's an example. Phi, as we saw earlier, was a linear function, simple linear function. This is a shape function. This is at node 1, this is at node 2. D phi is a derivative of a simple function, becomes even simpler. The integral is also very simple. When we plug it into the matrix, we see that we get very simple components of the matrix. We have the constants outside of the matrix, and we have the two nodal values of the unknowns on a vector. On the left-hand side, we have the boundary values as a vector at the nodes on the right-hand side, and the forcing function also as a vector at the right-hand side. When we assemble the matrix for the entire object, we come up with a matrix that has n by n rows and columns, and these are the number of nodes in a system matrix. We have here two elements, 1 and 2. Each element has two nodes, 1 and 2, 1 and 2. But globally, this node is 2, this node is 3, this node is 1. So node 2 of element 1 is global node 2, and node 1 of element 2 is global node 2. Then these equations, algebraic equations, can be formulated by assembling the element matrix into the global matrix. So here is the exact same matrix as we saw earlier, and it is embedded inside the global matrix. This is global node 1, global node 2, and the second equation for element 2 is similar to what we had before, but located at node 2 and 3. This is line for node 2, and this is line for node 3, so the matrix is placed globally in this location. When we assemble the matrix with all the elements and sum them up, then the formula or formation of the final matrix equation is being derived. It can further be simplified, and over here I added the expression that show where these terms are coming from, and this is the final form that we can use for the solution. The algebraic equations can now be solved, and the result can be represented and displayed in pictorially and in graphics. What I did over here is I developed the exact solution on Excel. It's not continuous quite. There is an element size of 0.1 going from 0 all the way to 1. This column represents the exact solution for each one of these elements, and the second column represents du. This is the difference between 2 points, and du dx is this value divided by dx, which is given in size, and then lambda du dx is also calculated. Plotting it shows us the exact solution. Then there are a set of system parameters which are being used to calculate this function. And then we go over here with the finite element formulation as we derived it, use the global matrix over here in Excel spreadsheet, going through the solution process and finding what is the values at global node 2, which is at 0.5, and global node 3, and the other unknown is the value of q at the first global node. And when we look at the results, we see that the value of the unknown at u2 is exactly the same as the exact solution, 1.125, and similarly at the value of 1 is 1.5 and 1.5. The value of q, the unknown value of q, is found over here is 0.25, and over here was 0.05. When we change the values of the system parameters, we get a different solution, exact solution. But when we go through the finite element analysis, again we see that at U2, which is 0.5, we get exact solution as the finite element approximation, and similarly at x equal to 1. And the unknown now is minus 2.5, it's not exact, versus minus 3.7. And again, this is because we discretize both the exact solution in order to see the effect over here. And this is the finite element representation of the derivative. And finally, when we change it once again, we get a different type of solution, but still the numbers are the same, much larger. At U2, the value is 87.5, both exact and with finite element. U3 is 180, and the value of the derivative at node 1, which was unknown, is 14.3 versus 15.5. This concludes our presentation, and we will now use the finite element software programs in order to solve real fluid problems. Thank you.